Hi, this is Greg from Structural Toolkit, and this is the second video in our two-story residential house design series. In the previous video, we went through a general introduction to our house, along with setting out all our structural beams and columns on the upper roof, the first floor and lower roof, and also the raft slab setout. This video will cover wall bracing loads and its distribution around the building, along with design in accordance with AS 1684/2021. If we end up needing a steel brace frame somewhere due to insufficient bracing walls, we'll cover it in a video later in the series. Brace frames will often link into the floor or roof beam design, and so it will be more appropriate to tackle them once we get to that stage of things. Bracing in a timber framed residential house typically comprises of evenly distributed tensioned metal straps, plywood or hardboard throughout the external and internal walls. Steel brace frames around openings and windows or brace frames within a wall are also sometimes used where there isn't sufficient wall length for standard bracing to work. It is also worth noting that there are other manufactured proprietary solutions out there, such as steel brace trusses or timber brace frames, but we won't be looking at any of those in this series. The bracing design of a timber framed house like this can be broken up into several steps. The first step is to determine the ultimate wind pressure, which we will do using Structural Toolkit, an engineering design software. Next is to then work out the load areas in each direction of the building for each floor or upper roof. These areas are typically set out based on where our bracing walls will be. We'll talk about this more when we get into our design. Once we have our load areas, we can multiply this by our ultimate wind pressure and coefficients to arrive at our design forces for each section of the house. At this point, you would then start to set out standard bracing throughout the walls of the house to match or exceed these design forces. During this process, it will then become clear whether either a brace frame is needed or if the design approach needs to be reassessed slightly. Using our two-story house, we will go through each of these steps in detail. So for our first step, we'll be starting in Structural Toolkit. Before we look at the wind loads module, we'll also want to take the opportunity now to set up our project properly. So we'll start by saving our project in an appropriate place. Then setting up our COM page header with our project details. We would then want to create all our sections to the left here to organise our project. To keep things simple and clear while we are going through the design, however, we'll create our sections as we need them. So our first section will be wind. With our section created, we can now open up the wind loads module. We went through this module in detail in our wind analysis video, so check that one out for more details. Before we start, we need to have a discussion regarding bracing that is outlined in AS 1684.2, Residential Timber Framed Construction for Non-Cyclonic Regions, AS 1170.2 for wind loads, and AS 4055, wind loads for housing. AS 4055 is applicable for NCC Class 1 and 10A structures, that is a house, and non-habitable structures like a garage, and comes with a number of geometric limitations such as eave heights being less than 6 metres, a maximum of 8.5 metres to the top of the roof, a width excluding eaves of less than 16 metres, and a maximum of 5 times the width in length, along with a pitch of 35 degrees. Outside these limits, AS 1170.2 needs to be used to derive wind forces. The wind speed derived from 1170.2 can also be applied to Table 1.1 of 1684 to get back to an N1 to N4 classification like 4055 produces. Using more tables within 1684, you can then derive a wind pressure on a surface which includes the surface coefficients. However, instead of this, we'll be using AS 1170.2 to derive our wind pressures, and with the application of surface coefficients from the same standard, then apply our ultimate wind pressures to a tributary wall and roof area to derive a racking force for a brace wall. We won't be covering the use of 4055 and 1684 for the derivation of racking forces, as using 1170 allows for the design of any structure whether within or outside the limits of 4055. As discussed in the previous video, our house is part of a new subdivision in Melbourne's eastern suburbs, so we can leave our location as Melbourne. Our importance level will be 2 for low-rise residential. Our design working life is fine as 50 and APE for serviceability of 25. Going down to the bottom, we can then put in our average height, which is the average height of our roof. To keep things simple, we'll use the ridge height of the upper roof, which is 8.2 meters from ground level. Our terrain category is then going to be based on the average category within the greater of a 500 meter or 40 times the average height radius of our site, including a lag distance of 20 times our height, which in our case will be roughly 160 plus 500 meters. Using Google Maps, we can overlay a 160 meter radius circle with an additional 500 meters beyond that in paint and get an idea of what kind of average terrain we will have. We can clearly see within our circle nearly all of the area comprises of suburban housing, which is associated with a category of 3. So this will be an appropriate category to adopt for all directions. Next we have our shielding factor. As a general rule of thumb, this will be 0.9 when surrounded by other suburban housing, but it's always important to consider the actual location of the house in question, as it may not always end up at this value. To give us a good idea of this, we'll have a go at calculating it ourselves. We can do this in Toolkit by opening the Terrain Changes module. And going to the Shielding tab. We can straight away plug in our height of 8.2 meters. The area we're designing in is pretty flat, so we'll leave our upwind slope as 0. Now the number of shielding buildings refers to the number of buildings upwind of our house with a height greater than or equal to our height of 8.2 meters, that are within a 45-degree segment of a radius of 20 times the height. This radius is 164 meters in our case. If we look back on our map, this might look something like this. Having a look again at Google Maps in 3D, what we're going to be looking for is buildings that are about 8.2 meters or higher. A good place to start is in the west where our critical wind is coming from. In our case, there appear to only be a few two-storey buildings, with a couple extra here that have been recently built that we can't see on the map yet. All of them appear to be similar in size, being about 10 to 15 meters long. The important length here is the length normal to the wind direction, so north to south in this case. What we'll do is start inputting them into our design and see what the shielding factor looks like. There are about 4 two-storey buildings in total in our radius, and so we'll start with that. To keep things simple, we'll say the height of each of these houses is 8.2 meters and their breadth is 12 meters. With all 4 buildings filled out, we can see that our shielding actually comes out to be exactly 0.9. On the basis of this, it would be reasonable to conclude that we'd probably arrive at a similar answer in each of the other directions. Even if this were not the case and you could only get 0.95 shielding in all other directions, you will still arrive at the same wind pressure as we started with our critical west direction. For our example here, we'll go with 0.9 in all directions. Our last input is then our topographic multiplier, and given we're in a fairly flat area, we'll leave this as 1. This then gives us our ultimate wind pressures in each of the 8 wind directions, which are then reduced to 4 values in the structure's 4 orthogonal directions, north, south, east and west. Although you can use the 4 orthogonal wind pressures for all your designs, for residential design you could simplify things by using just the critical direction, which is a conservative approach. If further refinement of a design is required, then this is often part of the design that is reassessed. For our bracing, we'll be using our critical wind pressure of 0.68 kPa for each direction, and can now go back to our CAD drawings. What we'll now want to do is work out our load areas and then the wind force in each direction of our house. Now what the general premise of this is each face of our house will be subjected to our wind pressure. What we want to achieve here is to design a system that will transfer the wind loads over the building all the way to the ground. In simple terms, the way this will work is our forces in the upper roof transfer via bracing straps provided by the truss manufacturer or engineer for where rafters are used to external and internal upper braced walls. These braced walls then transfer the forces into the floor structure where they diaphragm through the stiff flooring out to the lower external and internal brace walls, where they are finally transferred via lower wall bracing into the slab at ground level. This mechanism works based on there being an evenly distributed amount of bracing resistance throughout the house in both directions. You can find this discussed in AS 1684.2 in section 8. The approach to then designing this mechanism of force transfer is to go level by level, starting with the top part of the upper floor, walls and roof. As covered in 1684.2, the forces in the upper floor will be based on an area from the top of the roof to half the height of the wall, being half the floor to ceiling height. As the forces in the upper walls will then transfer down to the lower walls, we can then understand that the forces in the lower walls will then be the area from the top of the roof all the way down to the half height of the lower walls. With that out the way, we can now look at actually working out our bracing loads. Before we get into the areas, we'll first want to work out our actual ultimate wind pressure with coefficients applied. To do this, we'll apply both our windward and leeward external pressure coefficients coming from 1170.2. As our height is less than 25 meters and our building is on the ground, our windward coefficient is 0.7. As for our leeward, this can vary from house to house. A commonly taken value is 0.5. If we actually look at the table from the code, we know our roof pitch is a standard 22.5 degrees. We know our D on B ranges from 0.5 upwards, depending on which direction we look at. So we'll fall somewhere between 0.4 and 0.5 in our case. So taking the common value of 0.5 is a reasonable approach. These values multiplied by our wind pressure gives us an ultimate pressure of 0.816 kPa. Next, we'll take note of our floor to ceiling height, as there is a requirement in the code that a reduction shall be applied to any bracing capacities where the height exceeds 2.7 meters. For our top floor, this isn't the case, but it will become important when we look at our lower walls, which are 3 meters high. With these values covered, we can finally start setting out some areas. What we've got here is a template to help with drawing out and calculating our bracing forces and capacities. Now, to make sure we cover the requirement that the bracing is distributed somewhat evenly across the house, rather than just taking the total area in one direction and specifying enough bracing to meet the resultant force, what we will do instead is break down our area into multiple areas in one direction. Getting a feel for how to set out areas does take a bit of practice, but the general idea is that we will want to centralize areas around walls we will use for bracing. This idea should become clear as we progress along. With that said, you don't want to create too many areas, as not only does it increase the design time, each additional area division typically has diminishing returns when trying to arrive at an efficient bracing layout. There are many ways you could go about deciding these areas. What we'll be going through is just one method. So starting with the upper floor, we'll begin by drawing some lines at the boundaries of each end for our first face. The next step is going to be to draw our lines along the walls we can use for bracing. We will begin by drawing along all of them so this part makes the most sense, but as you get a feel for how this works, you'll often be able to skip several parts of this process. The next part is to then draw lines midway between each of these lines which will make up the edges of our area. By doing it this way, we'll get areas that have the brace walls at their centre. Once you've drawn out all the midway lines, you can then delete the internal lines over the walls. Now, if we were to draw areas about these points, we would end up with way too many areas. For something of this length, 3 to 4 areas are going to be more practical. One way we might be able to do this was by starting again and reducing the number of lines of the bracing walls, or alternatively we could keep our current lines and try to merge some of the areas together. By doing this we can appropriately balance the areas. Next we can then deal with the other direction. Given the width of the front face, two areas will do the job, and so we'll just split it down the middle. What we can do now is draw in our lines at the midpoint of our upper walls, which will be the bottom of our areas, and then go ahead and draw the areas for each section. With all our areas drawn out, we can now note down the areas for each. We can then multiply the areas by the ultimate wind pressure to get a force for each area, which if we remember is 0.816 kPa. So for example, our first area here is 15 meters squared multiplied by 0.816, which equals 12.2 kilonewtons. Rather than calculate out each area one by one, we can use the spreadsheet document in Toolkit to quickly calculate multiple. Particularly with bigger jobs, this can reduce some of the tedium and calculation errors. So with all our forces calculated, we can now look at actually laying out some bracing for the upper level. 1684 provides numerous types of wall bracing that you can use. For our design, we'll be looking at 4 types. Our first type, which we'll designate as type 1, are diagonal bracing straps, coming from table 8.18d. These give us a capacity of 3 kilonewtons per metre, but are limited to 1.8 to 2.7 metres in width. Type 2 is F11 plywood that is nailed to the top and bottom plates and noggins, being from table 8.18g. This type gives a capacity of 3 kilonewtons per metre as well, and can be no shorter than 900 millimeters. You can technically go as short as 600 millimeters, but further reduction factors are required, so it is usually avoided. Type 3 is hardboard nailed to the top and bottom plates and studs. This only gives us a capacity of 2.9 kilonewtons per metre, but can be used for walls as short as 460 millimeters. Finally, our type 4 is plywood like type 2, but is slightly thicker and also requires additional hold down fixings. This gives us a capacity of 5.2 kilonewtons per metre, and like type 2 can be no shorter than 900 millimeters. Note the values for sheet bracing types 2, 3 and 4 assume a low joint group of the studs of JD5. However, these can be increased slightly if using JD4 timber as per clause 8.3.6.3. In the previous 2010 standard, the bracing values were for JD4, and if JD5 was used, a reduction needed to be applied. For our design, we'll be going with the conservative values. Ideally, we'll want to be using as much simple type 1 as possible, type 2 where type 1 doesn't fit, that is walls less than 1800 millimeters long, and type 3 where type 2 doesn't fit, being walls less than 900 millimeters. We would only use type 4 if absolutely necessary due to the additional requirements for hold down fixings, especially when fixed to a timber floor. However, fixed into a slab, the additional requirements are not so onerous. Now that we know what bracing types we will be using, we can look at the positioning of our bracing. AS 1684.2 states that bracing should be evenly distributed and should initially be placed in the external walls and where possible at the corners of a building. Internal brace walls should be situated close to the external walls as well. Parallel bracing walls must also be no more than 9 meters apart according to 1684. So we'll start with our area on the far left here. At the corners we don't have enough room for type 1 or 2, so we'll place in 750 millimeters of type 3 at each end. We'll be showing the bracing on the inside face of the walls, however in reality they are typically on the outside. We just do this to maintain clarity of the drawing for the builder. This amount of bracing alone won't meet our force, so we'll add some type 1 at each end in these two internal walls. 1.8 meters for each should do the job. If we then add up the total of this bracing, we'll end up with 15.2 kilonewtons, which meets our force for the section. Moving on to our next section, we have several long walls to pick from. We could just put 4 lots of type 1 bracing sections in here, but this might be a bit excessive. Thinking ahead, we can see there's another internal wall to the next section at the southern face. So what we can do to keep things spread out is to just use 3 lots of type 1 bracing, with 2 at the north and 1 at the south. This gives us a capacity of 16.2. Finally, in the far right section, we'll place 2 type 3 like we did at the other end in the corners, and also a type 1 in the internal wall. This gives us a capacity of 9.8, and with that we've finished the north to south bracing of the upper floor. Next we can deal with the east to west. Keeping with the same idea, we'll put some bracing at each corner using type 1. This will give us 10.8 kilonewtons in each section, meeting our force requirement. As the width of the upper floor in this direction is only 7 meters, we won't need to look at adding any intermediate bracing between. And now our upper floor bracing is complete, so we can move on to our lower floor bracing. Here we'll go through the same process, beginning by drawing out our lines along the main walls we plan to use for bracing. We can then draw central lines between our initial lines like before. And finally we can clear out the initial lines and also merge any areas that are probably too small. With all our lines ready, we can go ahead and draw our areas and calculate our forces. You'll notice there is a step in our areas, and this is due to a floor level change. So with our forces ready, we can get into laying out our bracing. As we discussed previously, the lower level needs to also transfer the forces from the upper walls, so we'll be dealing with much higher forces. Starting with the north to south, at the far left we'll need to reach 18 kilonewtons, but don't really have much wall to use, meaning we'll probably need to go to type 4. In the south we have 1.8 meters, and we'll put some type 4 here. As type 4 requires additional hold down fixing, we'll give it a different colour to make sure it stands out on our drawings. Adding 1.3 meters to the north corner as well, we get a total bracing capacity of 3.1 times 5.2, which is also multiplied by our reduction factor of 0.9 due to the walls being 3 meters high. This only gives us a capacity of 14.5 kilonewtons, being 3.5 below our 18 kilonewton force. There's a few ways we can deal with this. We could use a steel brace frame, which is one of our last resorts for bracing. We could try and readjust our bracing areas, or we could justify the transfer of forces to other brace walls in the lower floor. Given we aren't dealing with a substantial amount of load, trying to transfer the load elsewhere is probably a good option. To see how we can do that, we'll put some bracing in the adjacent area first. In this area we have to deal with 23.6 kilonewtons of force. This time we have plenty of wall length to utilise, but we will probably still need to use some type 4 bracing. To help with absorbing some of the load in the adjacent area, we'll want to use walls as close to the area as possible, so we'll put some type 2 in the shorter wall here. Now we probably can't put type 1 in both of these long walls and reach our design force, so given that type 1 has a maximum length of 2.7, we'll put some type 1 in the shorter of the two and then type 4 in the longer wall. This gives us a capacity of 28.8 kilonewtons, including our 0.9 reduction, which is over 4 kilonewtons above our design force. Now between our two areas we have a large continuous area of floor framing, so we can justify our bracing here by recognising that our floor will allow some diaphragm action, allowing the 3.5 kilonewtons force to transfer further into the building. To designate this on our diagram, we'll have an extra transfer road below. When we do this transfer, we need to be aware that the force will result in a moment couple and an equal and opposite force generated in the north and south walls. We can determine this magnitude by taking moments about the bottom left, which is 3.5 by 6.9 on 8.3, giving us 2.9 kilonewtons in the north wall, and to maintain equilibrium we'll have an equal and opposite 2.9 in the south wall. When we do the bracing from the other direction, we'll see this should be easily catered for. Going to our next area, we'll start by placing in multiple sections of type 1 and type 2 in the shorter wall here. We won't use type 4 here like we did on the other side of the wall, as we should be able to reach our design forces with just type 1 and 2. With this arrangement of bracing, we get a capacity of 21.3 kilonewtons, which meets our design force. An important thing to remember while we are in this area is that you can't use cavity sliders for bracing, as they don't comprise of the stud framing required to fix the various bracing types, effectively being non-structural portions of the wall. So keeping this in mind, it's always important to locate any cavity sliders when setting up your drawings. While we're on this topic, something to also be aware of is any wall recesses or alcoves in rooms like bathrooms, which will also interfere with bracing. You also need to consider the placement of bracing on bathroom, laundry and kitchen walls, which require penetrations. Stair voids are another area to think about, as the floor level above may not be restrained and so will often not be an appropriate place for bracing. Next we have our final north-south bracing area. This time we don't have a lot of wall we can use. We can put some type 3 bracing down here, which will give us 3.9 kilonewtons, meaning we come up just over 8 kilonewtons short, which with the amount of wall remaining in the garage definitely won't be enough. Transferring over 8 kilonewtons, which is almost 70% of the area's force, is probably a bit too ambitious, especially since the next wall inwards on the north side is almost 6 meters away. Sometimes using strategically placed bracing straps in the roof or floor structure may be sufficient, but we need to keep in mind 1684's requirement to have evenly distributed bracing about the house. So the most appropriate solution here will be a steel brace frame over the garage. Designing a brace frame has a bit more to it than just setting out some standard bracing, and its design will be integrated into the overall framing design of the house, so we'll be covering it in a later video. For now, we'll just designate it as taking 8.3 kilonewtons of force. At this point, it should be pretty clear how we will go about the rest of the bracing design, so we'll skip ahead and summarise what we'll do for the east to west direction. Here we have our bracing completed going east to west. At the eastern end, everything is pretty standard. We've got our bracing at the corners and along some central walls. In one of the garage walls, we needed to put some type 4 in, as there were no other walls in the area. Something you may have noticed is that at the western end, there aren't really many walls that we can use for bracing. Under a situation like this, it may be possible to meet our design forces for each area, but then all the bracing ends up in one end. This goes against the idea of evenly distributed bracing throughout, and so to address this, we have upped the corner bracing here to type 4 to ensure we'll have appropriate bracing capacity at this face. With that complete, we now have our standard bracing complete for both levels, with our one brace frame to deal with later on in the design. What we might do now is have another look at the overall bracing and perhaps add a few other areas to ensure an even distribution. In our case, we've now added an additional short type 2 and 3 braces on the north and south face of the lower level. With the bracing layouts in a block, we can transfer them to our drawings. At this point, we might tidy up the bracing drawing page, such as adding a note that specifies the need for additional hold down for type 4. This way it will be clear to the builder. With our standard bracing complete, we can now move on to our roof framing design, which will be part of the next video in this series, where we'll go through our upper roof framing along with column design. If you have any questions, feel free to contact our support team via email or by calling us. Thanks for watching.